Thanks for coming, everyone. As Fahim said, I'm the CTO of Stormforge, background in applied maths, machine learning, but working with Kubernetes for the last 6-7 years, focusing mostly on autoscaling and sort of resource management, managing resources in Kubernetes. So first of all, why does autoscaling matter? And the whole point of autoscaling is to have the right resources at the right time. And then it comes down to a key trade-off. You need to make sure you have enough resources that you can ensure performance and reliability, but not so much that you're just wasting huge amounts of money and running extremely inefficiently, which is very common in the cloud and can get very, very expensive. Autoscaling, not new to Kubernetes, been around for a long, long, long time. And when people were working with VMs, it typically came in two different flavors. First, there's vertical autoscaling, which is just, okay, I'm going to run it on a single machine, but I'm going to make the machine bigger and bigger and bigger, which works great up until the point where the machines can only get so large, and then you need to start splitting it up and running multiple replicas, which is then horizontal autoscaling. And then the idea is you can scale it out much, much further, but you need to have other considerations. For example, how am I going to balance traffic between the replicas? What's the right time to scale up and add a new machine, etc. So Kubernetes has both of those, and then it has a third dimension, which is new to Kubernetes cluster computing, which is cluster autoscaling. And then the idea with Kubernetes is you're going to run lots of pods, lots of containers on the same node in the same cluster, and then how do you decide, okay, given these pods, I need to run these pods, what are the right nodes to run it at any given time? And how do I add and remove those? So there's three different dimensions, and then for each one, there's a variety of tools. There's a lot of tools which were built directly into Kubernetes from sort of day one, and then a few more advanced projects which came along sort of maybe 5-6 years into Kubernetes lifetime to try and make some of the sort of more difficult use cases a little bit easier to manage. All right. So let's start with horizontal. So the idea here is that you want to add replicas when the usage on your application goes up and spin them down when it goes down so that you can sort of take advantage of the elasticity of the cloud and run efficiently and performantly. So there is a HPA, the horizontal pod autoscaler, built into Kubernetes. And then the general idea of how it works is first you have the metrics server, which provides the sort of monitoring pipeline built into Kubernetes, tracking things like what containers are running, what are they requesting, which is what size of the pods, of the amount they're requesting, how much they're using, etc. So the HPA is constantly querying the metrics server to see, okay, what needs to be scaled, how is it doing, etc. And then, wrong way, it makes its calculation and then updates the replica count on whatever object it's managing. And pretty much all of the objects built into Kubernetes work with the HPA. Stateful sets, deployments, and then you can also, if you're working with custom types or building your own custom resources, you can also implement the scale sub-resource, which means you can have the HPA, even though it's built into Kubernetes, anything you build can be compatible with it. So it queries the metrics, updates the replica count for that object, and then that object is responsible for spinning up, spinning down, and actually rolling out the changes suggested by the HPA, which for the deployment means talking to the replica set it manages, which will then add an additional pod. So that's how it works sort of from an engineering point of view, but the key step is really how is the HPA deciding what the right number of replicas are. And then there's been a bit of an iteration. The first version of Kubernetes, or the first version of the HPA into Kubernetes, allowed you a single option. All you could do was scale on CPU utilization. So we have a little sketch of it here. Each of the dashed lines is a container, and then you can see, you get can you see my mouse? Yeah, just about. So you have a container which is sitting around not doing very much. It gets a sudden spike in traffic. It gets very close to using all of the resources it has. With the HPA, the key thing you have to consider or to configure is the target utilization, which is what utilization to start adding replicas at. So it gets significantly over the target utilization, another container is spun up, and then it starts sharing the load, and you end up with two things sharing the load at the desired utilization. And then the maths behind it is pretty simple. you look at the current utilization and take the ratio of that and the target, and then you say, okay, if my utilization is 2 times too high, then I will add twice as many replicas. So it works pretty well, and this is typically why people start with horizontal autoscaling, just because it's simple and everything you need is built into Kubernetes. And this was all they allowed in V1. And then with V2, they literally provided every other option possible under the sun. So you can scale on custom and external metrics. So imagine you have Datadog metrics measuring latency, error rate. You can scale on that. Queue depth, if it's some sort of batch queue, literally anything you can scale on, as long as you can actually do the plumbing to get that metric into Kubernetes. You can scale on multiple metrics. So you could scale on queue depth, but you could have a backup scaling metric of CPU utilization in case one of the pods goes a little haywire and you need to add more capacity. And you also get very, very detailed control on policies to scale up and down. So you can say, okay, on the way up, don't add more than 4 pods at a time, or don't add more than 50% of the replicas at a time. So you could go 2, 3, 5, 8, and then you could make that different on the way down. For example, sometimes if you scale them up, you don't want to scale them down for 10 or 20 minutes in case it's very bursty, and you get another spike a few minutes later, and you don't want to thrash the pods. So extreme amounts of control, and you can do a lot of very powerful things with this. So what I'm showing here is a great example from a KubeCon talk a few years ago by Shane and Will. Will works for a hosting platform called Acquia, which runs Kubernetes at large scale. And then one of the things they need to do is scale their workloads up and down for customers. And initially they did this on CPU utilization, and then they realized that that was an extremely poor fit for their workload. It just didn't show, CPU utilization wasn't a good metric of the actual load on their app. It was doing a lot of network connections, so the app was under load even though it wasn't using CPU. They had spent a lot of time trying to fine tune that target utilization and not really found a good answer. So they put in the work and they decided that they would switch over, and they would switch to a custom metric, which is, okay, I have 8 processes in my web server. Once 4 of them are on average, 4 of them are in use for any given pod, add more pods. So it's extremely tightly coupled to what the actual load on their application is. And can anyone guess the moment they cut over from the old CPU utilization metric to the new custom metric? Shocking no one, it's right here. And what they found was it became significantly more stable, and they weren't endlessly thrashing the application. And obviously also cheaper as well because the average replica count has gone down. So even though V2 of the HPA can be very complicated, CPU utilization is very rarely a good metric. It can be good enough, but it's rarely good. And often finding the right thing to scale on is worth the time and the effort. Out of interest, how many people here have actually gone through that journey? Started scaling on CPU utilization, switched to a custom metric. Anyone regret it? No. Typically works out pretty well. It's worth the effort. However, the effort can be very high. You have to do a lot of custom work to plumb metrics from whatever Datadog, et cetera, you're using into the Kubernetes monitoring pipeline so the HPA can access them. There's often things like authentication. If you want to talk to Datadog, you need to have API keys to do that, et cetera. So even though it was typically a much better approach to use custom metrics, it can be painful, which is where the next project, open source project, which has been around for, I think, 3-4 years now, Kada, comes in. So the goal here is just to have a whole bunch of off-the-shelf scalars pre-configured for you. And Kada will do all of the, basically, plumbing and just provide a higher level interface which people can use to get these custom metrics up and running. So they have a catalog of 50 plus built-in scalars, lots of things on, lots of common sort of tools like Kafka, RabbitMQ, things like AWS, SQS, so the simple queue service, there's stuff for Azure. Most things you want to scale on, they probably have a pre-built option for. They also have a whole bunch of authentication providers so that you can do authentication to Amazon, Azure, a variety of other things. And then most of it is just providing a simpler interface to the HPA. The one really, really, really nice feature they have, which the HPA does not support, is scaling to 0. So we use this at Stormforge. On the back end, we're running a machine learning task queue. So tasks get put in RabbitMQ. We have a whole bunch of workers which pull off that. Scaling that on CPU utilization proved to be basically impossible, at least to do reliably. So now we use KDA and we scale on queue depth. And when there's no tasks, machine learning is expensive, we spin it all the way down to 0 and then get significant cost savings. And we've seen a lot of other people have success with this sort of scale to 0 approach. It's a really nice feature of KDA. And then KDA is also extensible. So you can write your own. They have the 50 plus built-in versions, but you can write your own. You can make it do whatever you like. So the perfect balance of sort of happy path, easy to use, but total flexibility in case you run into an extremely unique use case. And then the diagram here shows how KDA works. So it has all of these components here, which are responsible for doing the authentication and the plumbing. The metrics adapter is what is going to feed that metric server, the monitoring pipeline in Kubernetes. And then KDA will translate what you tell it to do. It will create a HPA object that it manages and configures for you. And then when it's scaling from 1 to some number greater than 1, the HPA just takes over. So KDA is not actually doing anything except configuring the HPA to then behave as required. With the exception of scale to 0, it will override it and just scale it to 0 directly. So that's horizontal. Next is cluster. And typically, the reason I have it structured this way is the whole point of cluster autoscaling is to add and remove nodes as the number of pods changes. And normally the thing which is driving the pods to go up and down is some sort of horizontal autoscaling. So the original tool to do this in Kubernetes is the cluster autoscaler. And what this does is you configure autoscaling groups in your cloud provider of choice. So on AWS, it would be autoscaling groups talking to EC2. And then for each of those autoscaling groups, you pick instance type. And then depending on the different use cases you have in your cluster, maybe some need memory-heavy nodes, maybe some need CPU-heavy nodes, maybe some can work with spot instances. You end up typically with, we see people with dozens of autoscaling groups. And then the cluster autoscaler constantly watches pending pods. So Kubernetes, a pod gets created. The scheduler goes to find a node that it can fit on. And if it finds none, it will mark it as unschedulable. The cluster autoscaler uses that as a sign to say, OK, we need a new node here so that we can schedule this pod. Picks between the different autoscaling groups. People don't typically look at it. You can customize the behavior, how it picks between the autoscaling groups. If they're mutually exclusive, that's not a problem because it should only fit on one. And then it will start a node, the scheduler will assign it to the node, and then the pod, which was previously unschedulable, will now be running. Works very well, available on basically every cloud provider you can find. However, it has a few downsides, and most of it comes down to just how much effort you have to put in to configure all of these different components, all of the different autoscaling groups outside of Kubernetes in your cloud provider, and just the configuration overhead forced on you by the fact that it's very much a one-size-fits-all. Each autoscaling group can only have a single instance type. So that's how it adds nodes, and then the other key part to be cost efficient is how you remove them. So the way cluster autoscaler does this is it sets a threshold, and then for any individual node, once you get below that threshold, that node will be cordoned, all the pods will be evicted and rescheduled elsewhere. So you can see a sketch of that here. 6 nodes, that one, and that one are below the threshold, so they will be deleted, and then the pods will be rescheduled. It provides an extreme amount of customization about how often you should check, what the threshold should be, all sorts of stuff. And you can also annotate nodes to say, OK, don't touch this node. Imagine you have, I think Andy talked earlier about the singleton which can't be touched. Whatever that's running on, you don't want to be turning that node off, so you can override the cluster autoscaler. So what will happen here is the 2 underutilized ones will get spun down. The top right is underutilized, but is exempt. And then you end up with fewer nodes, higher efficiency. So the cluster autoscaler has been around for, 7 or 8 years now. But a new tool was released by AWS a few years ago, which we've seen a lot of people using. to replace the cluster autoscaler, and we found it to be just amazing. So the tool is called Carpenter. It's open source, and just like the cluster autoscaler, it has a provider model where there's the sort of core logic, which is cloud provider independent, and then there's the sort of integration. Each cloud provider can build its own provider. AWS open source built it and open sourced it. They built the first provider. It's now available on Azure as well, and I don't know about future ones. And it has a few benefits. First, it is significantly faster and more responsive than the cluster autoscaler. So if any of you have ever worried about horizontal scaling and worried about the edge case where you go to scale up, you go to add a pod, and it doesn't actually fit on your cluster, and then suddenly what used to take you 30 seconds to start a pod takes 5 minutes because it takes 5 minutes to start a new node. Carpenter can start nodes. At StormForge, we also use Carpenter. We found that our node start time went from several minutes to about 60 seconds when we switched to Carpenter. So it's significantly more responsive. It does away with that one-size-fits-all approach of the cluster autoscaler and moves all of that configuration out of the cloud providers into Kubernetes, which just makes it much easier to manage and work with. And then it does a much better job of the ongoing consolidation than the example I just showed for the cluster autoscaler. So first, the startup. So the reason Carpenter can start things so much faster is because it eliminates a lot of the jumps to go from, okay, I have a pod which is unschedulable to I have a new node. So as we discussed before, cluster autoscaler will watch pending pods, it will pick an autoscaling group, it will tell that autoscaling group to scale up, which will then talk to the, in AWS language, EC2 API, which will start a node. And the issue there is that can be very slow. This is one of the main reasons it takes so long to start a node, just because of all of these hops. It can also be a little bit brittle, because if that autoscaling group runs into an error, frequently the error will not filter back to Kubernetes, and you will not know why you failed to get a new node. So Carpenter eliminates that and just goes straight from, okay, it works with the EC2 API directly, it sees a pending pod, and creates a new node. So that's why it can be so much faster. It's also why it can eliminate that sort of, okay, autoscaling groups tied to a single instance type and be much more flexible and not have that sort of group-based approach that the cluster autoscaler does. So here's an example of scaling up. So you have the HPA, it's adding pods. You have 4 existing nodes. The scheduler can't schedule all of them, and we'll need to add a node. So what you will end up getting is this. So you can see the 3 orange pods. There was space on existing nodes, so those pods just got scheduled. And then this green pod was too big to fit on an existing node, so it triggered, okay, we need to put a new node, and then the 2 other blue pods got included with that. And then I should highlight, Carpenter works with all of the sort of scheduling logic options built into Kubernetes. Taints, tolerations, pod affinities, node affinities, etc. Okay, so that's on the way up. So you want to start adding resources on the way up, but you also need to make sure you remove them as the load starts to drop. And the way Carpenter can do this is significantly more powerful than the cluster autoscaler. So first of all, look at this configuration here. There is a lot of waste on this new node, and then some also wasted on this node. So what it's going to do is it's going to say, okay, I could move this green pod over here, and then I can reassign the blue ones. A lot of them will fit on the new node, and then there was some space on the other node as well. So what's happened here is you've gone in, and then you've removed 2 nodes, and you have 1 node. And each of those nodes is better bin packed, high utilization, cheaper, without sacrificing any reliability. And then imagine the load starts to, so that was just, okay, for a fixed amount of load, a fixed amount of resources required, how can we consolidate and use fewer nodes? But eventually, the HPA added pods, it will remove them as well. So we take those orange, pods, which are highlighted here, take them away, and suddenly these nodes are quite underutilized, and you could consolidate everything onto a single node. So Carpenter is just constantly sitting there, figuring out when nodes need to be added, and then constantly consolidating so that you can run more effectively. And I'll show a demo in a second. It won't all be just slides. And then the other big advantage that Carpenter has over Cluster Autoscaler is working with Spot instances. And there's a few reasons for this. First, it makes it much easier to tie into the Spot interruption feed, so you get AWS will give you a 2-minute warning saying, okay, you're going to lose this node in 2 minutes. It is very good at picking those up and evicting pods so that they can get rescheduled and run elsewhere before the node actually goes away. The second big advantage it has is because it can start the node so fast, often it can have the new instance up before the spot interruption period is up. So if you get a 2-minute warning, but it takes you 5 minutes to start a node, you have a 3-minute overlap, which is potentially very risky. If you get a 2-minute warning and you can have every single pod rescheduled before that 2-minute warning expires, that's perfect. And then you can run on Spot with basically zero risk of interruption. And then because it breaks that one-size-fits-all, it makes it very easy to interleave on-demand plus Spot instances and fish in a very wide pool and just look for every available type of EC2 instance and see which one is cheapest at any given time, which is often the way to get really good savings with Spot. All right. I think I said all that. All right, perfect. I'm going to do a quick demo. Can everyone see? Is that big enough? Is it too bright? All right. Let's see. That makes that bigger. All right, so I have a cluster with Carpenter. Yeah? Someone say something? No. So I said before that Carpenter lets you configure everything inside Kubernetes. So when you install, you get a custom resource that you can set up called a node pool. And then rather than specifying the exact instance type to run on, instead you specify what attributes you're comfortable with in the requirements. So here I've specified the architecture, the operating system, the capacity type on demand. I'll change that in a little bit. The instance category, so C is compute heavy, M is general purpose, R is memory heavy. You can say what generation you're comfortable with. Basically, you go in and just say, this is the box I'm prepared to live within, and then Carpenter will decide for you which one makes sense, which is the total opposite of the cluster autoscaler, where you need to go in and say, okay, these are the exact instances I want. I've set up an autoscaling group for each, and then cluster autoscaler does a crew job of picking between them. So you configure that. I have some workloads running. One is CPU intensive, so it's basically one core for 1 gigabyte. One is very memory intensive. And then if I look, this is always everyone's favorite part of the demo. I'm using a tool called EKS Node Viewer, built by the Carpenter team, basically to do demos like this. And then what you can see is the top 2 nodes are just running Carpenter, a few other sort of core control plane-like components. And then this node at the bottom is the one which is actually running my workloads. So I have one replica of the memory heavy, one replica of the CPU heavy. Apparently the cheapest way to run that is to put it all on one compute heavy instance, and then you can see it's much more, the memory heavy workload is pushing the utilization of memory much higher than the CPU utilization. And then we go in and we scale it up. So we add it to 10, and then, oh, there we go. It instantly starts a new node. And then what's interesting here is the original ones were running on a C6A large. The new workloads have the same compute-heavy sort of footprint, but they're or CPU-heavy footprint, but there's way more of them. So Carpenter has its options. It's going to use an extra large rather than a large. And then you can see the capacity type is on demand. It's coming up. Typically, it's a great test for actually demonstrating how fast Carpenter can start nodes. And while I do that, I can actually show the actual resources. So you can see the requests here. The memory intensive one, it's 2 gigabytes, 350 millicores. Let's see. and this has the reverse. The same amount of CPU, but about a sixth of the memory. And if we go back, it's typically longer than typically takes. There we go. So it started it, and then you can see that now the CPU utilization of this is much, much higher, and the memory is less, which makes sense because every single workload we added was a CPU-heavy workload. So now we do the same for the memory. So we'll add 5 replicas. And what you can see is there was a lot of memory free on that node we just started, the C6X large. So some of those memory pods which were added, 2 of those replicas fit immediately. So it has put them where there is space, and then it has spun up a new node to handle the other unschedulable pods. And even though it's a memory-heavy workload, it can fit it on a general-purpose node, leaving more space again, so that if there was to be a CPU-heavy workload, it would just fit in. And then I was going to show it. Oh, there we go. That was much faster. So that was 40 seconds. And if anyone's worked with a cluster autoscaler, can you imagine doing a demo like this? You would have to wait 5 minutes every time you hit a command, and the whole talk would have been 5-minute waits, which would be wild. How much time do I have? So I was going to show scaling down. I can show that quickly. So let's take away all of the CPU-heavy CPU-heavy workloads. What I suspect is going to happen is this big node, which was added when that was scaled up, will go away. And I think if I got my maths right, you can also take the workload from the C6A large, and there will be enough space on the M6A large. And then you will go from 3 nodes to 1 node, but it will be a node which is the right balance of CPU and memory heavy. Apparently I was wrong. I did not get my maths right. And then the final thing to show is using Spot. So, I should also highlight as well while it's doing that. You get a lot of control in the same way you can control. Carpenter is much, much more aggressive about spinning down nodes than Cluster Autoscaler. I think Cluster Autoscaler spins down one, waits 10 minutes, spins down another one. It takes a long time. Carpenter will be much more aggressive, but you do have control. So you can say, don't touch more than 10%, 20% of the nodes at a time. I think you can also set expiration on nodes. It has the same like label and annotate nodes so that you can control when they get spun up or if they get rolled a certain frequency. It has lots of, it's fantastic. Right, and then to show how easy it is to use Spot, all I have to do is go in and take the node pool, add Spot to the capacity type, and then it will use whatever is cheapest, which will be Spot most of the time, but if it runs out of Spot instances, it will just use on-demand, which is just so much easier than trying to do the analogous task with the cluster autoscaler, where you would need a new autoscaling group plus to tune the logic about which one to pick. And what we should see is one of these nodes getting cordoned, drained, and a Spot one coming in to replace it. There we go. There we go. And then we set the requirements that, of nodes we were comfortable with to be extremely broad. Obviously, you have control. You can change whatever you like. And apparently, an M7i Flex is the cheapest thing around in the Spot pool right now, so that's what it spun up. And it will just constantly do this automatically on an ongoing basis, consolidating, finding the cheaper Spot instances. And what people typically find is they get sort of 30-40% savings from using Carpenter versus Cluster Autoscaler. Okay. And then to go back to the talk, so we talked about horizontal autoscaling, adding and removing replicas, adding and removing pods. Cluster autoscaling, so okay, I'm adding pods, how do I add nodes to run those pods, and then I've taken things away, how do I consolidate and keep running efficiently? But cluster autoscaler and Carpenter, they are keying off unschedulable pods, and so they're at the mercy of the size of those pods. If all of your pods are set to be way too large, the requests and the limits are much too large, you will still be running extremely inefficiently. And the dirty secret of Kubernetes, or one of the dirty secrets, is people are horrific at setting requests and limits. Datadog did a survey. they took a look and saw what percentage of requests were actually being used. Half of pods use less than 25% of their resources, and it's kind of a mixed bag. Some are doing a little bit better, some are massively under-provisioned, which is very risky. So this is where most of the waste in Kubernetes comes from. When people are running, I think the average efficiency of a Kubernetes cluster is like 25%, and Carpenter can help with some of that, but this is the root cause of the problem. And then the question is, why don't people solve it? It's because it's very, very difficult to actually get right at scale. Everyone goes through the same journey. First they ignore it, and that goes away immediately when they have an outage. Then they're like, okay, we have to set this. This is risky. What value do we set them to? And if you have thousands of workloads, no one wants to do this 1,000 times, so they do a one-size-fits-all. And they will say they do t-shirt sizing, and they have different sizes of different pods, but if you ask a developer what their workload needs, they will always tell you the largest amount. Or they will tell you the exact same resources the VM that used to run it had. And that's great. It's reliable now, but it's typically very, very inefficient. That's how you get the behavior you saw on the Datadog slide, where everyone's using none of the resources they request, and then they decide they're going to go in and do it manually. And they'll have the engineers once a week come check, and we've seen many people try this. We've seen no one succeed. And the reason is engineers already have a lot of more valuable tasks to do with their time, and the platform team has to build tooling, support, education, etc., and no one wants to do it manually. We've seen lots of people try, but it's just doing it for thousands of workloads, it's just like a hamster wheel. So the only way to really fix it properly was with automation. There is a tool built into Kubernetes called the Vertical Pod Autoscaler, which will do this for you automatically. It has a wide variety of basically limitations so that no one uses it. So that same Datadog survey, they surveyed people's uses or usage of autoscaling tools. I think something like 60% of people were using HPA or CADA, 1% of people were using the VPA. It's basically unused. And that's because a variety of reasons. So at Stormforge, we have a replacement for the VPA. It has the balance of sort of the machine learning, the intelligence to pull data out of Kubernetes, say these are the right requests and limits, plus the automation to make it sort of roll it out on an ongoing basis. We've basically tried to take a lot of the limitations of the VPA and remove them, so we're compatible with all the other tools in your autoscaling toolchain. The VPA will typically fight the HPA, which is a problem. We make it much easier to configure. We make better predictions because we have machine learning. We're a little bit more careful about how we roll out the recommendations. We're not evicting pods or causing downtime. And then a variety of other things that I don't want to bore you with since it's a community event, but if you're interested, come to the booth, find us at the happy hour, and we'd love to talk. Oh, and we have a QR code. We have a free trial, a sandbox. You can come, install it, try it. If you do, our product team will probably reach out for feedback. We would love for people to give us feedback. It's unbelievably valuable. And yeah, I think that's it. I'll leave this up for the QR code. Any questions?
Yeah. I wonder, there used to be a tool called the Goldilocks that used to use the VPA and recommend changes to your deployments based on that. We still use it. Our developers still rely on it for manual, adjustments. How about that?
So Andy's smiling because I think the guy who created Goldilocks is at the back. The Goldilocks is great. It basically provides a UI and a few additional workflows to make it a little bit easier to work with the VPA, but I think it, just due to the limitations of the VPA, has to be a manual process. And if you're doing this manually, you're still in that third stage of that sort of setting request journey where you have to get developers to do it on a regular cadence, etc. We've seen people do that. They typically save 10, 15, 20%. It's great to go in and pick the low-hanging fruit, but we typically save people 50, 60% because we can do it automatically on a schedule, etc. So Goldilocks is great. It's built on top of the VPA, so it inherits all of its limitations. Andy, anything to add? No? Perfect. Yeah.
Um,
How do you resize pod requests without disrupting the pod? Are you using the in-place pod resizing beta feature, or what are you doing under the hood?
So we patch the workloads, and then we rely on Kubernetes to roll out those changes, just the same way you would if you're rolling out a new version of code. That's one of the ways I said we were a little bit more careful than the VPA, which will evict pods and then wait for them to get rescheduled, which is more disruptive. So we patch and we roll it out in the same way you would with any other change. No, if you patch the deployment, it will spin up the new pods with the new resources before spinning down the old ones and handle that sort of clear cut, that sort of smooth cutover, which is what Argo rollouts, deployments, etc. do for you. The in-place pod resizing, we're obviously very interested in that, and it would be great for us because then we can make more frequent fine-scale adjustments. My understanding is it's still in alpha, which means it probably won't be available in any of the cloud providers for a while, and has a bunch of fairly serious kinks to work out before I would recommend anyone use it in production.
Small question about the resizing. Sometimes I like to keep track on the repo on the changes. Is a way for StormForge to, instead of modifying it, to make a PR, so then we can keep track on the changes?
Yeah, so I highlighted it's two parts. It's the intelligence to make good recommendations, but also the automation to roll it out. With everyone using GitOps tools, we've got a variety of different ways we can integrate. We can make PRs. However, people typically don't want to do that because if you have thousands of workloads and you're changing the resources every day, it can be a lot of churn. And they don't necessarily need the resources for the last 12 minutes in the repo. We have that option. We also can use some of the features built into the GitOps tools to basically deconflict them. So we can make changes and we won't get overwritten, but you can then still keep safe defaults in case you have to redeploy a fresh cluster, etc. So yeah, we have a variety of ways of working with it, and that how do the developers actually adopt them is one of the key sort of challenges to be solved.
Thanks so much.
Thanks, Philippe.